Hey guys, and welcome back to the YouTube video. Now, as you can see, this is a bit of a different video since I am on my iPad. The reason is that today I am actually going to be taking a moment and explaining you something, and I just thought that doing it on the sorry for all of these problems. So today I'm going to be from today I'm going to be starting this quantum computing videos where I'm going to be posting a few quantum computing programming videos. But the thing is, the last time when I actually explained to you quantum mechanics, it was correct, but it was at a superficial level. And when I say superficial, I mean really superficial. It's not exactly, I hadn't exactly dived into the actual math. So today I'm actually going to be diving into a bit of a math. Now, if you think that this is irrelevant, I wouldn't agree. The reason is that quantum computing actually uses a lot of the maths that I'm going to be showing you. So since the quantum computing idea basically means all these superpositions and entanglement on all of this really correlates with the math we're going to be doing right now. So first of all, I want to tell you that the equation we are going to be looking at, the equation that actually governs the quantum computing and everything, is the Schrödinger wave equation. It is the Schrödinger wave equation. Now, what's so special about this equation? Why do we use it? This equation is pretty much governs the principles of quantum mechanics. All of the equations that you are going to be looking at, if you actually study quantum mechanics, are such as the Ehrenfest theorem, are all derived from the Schrödinger wave equation. Yeah, there are some equations which are not, but this equation is pretty much the I would just say it is the main equation of quantum mechanics. This equation is actually very powerful. The person who actually made this equation, Erwin Schrödinger, actually received a Nobel Prize. He was a Nobel laureate. Sadly, he died. It's kind of a long time ago that he died, and he's actually not that well known for some reason. He's actually one of my favorite scientists, but he's not that well known. But whatever. So he is the brilliant mind who actually made this equation. He's the guy behind all of this. And today we're going to be having a sneak peek at this equation. We're going to be solving the equation for a particle in a box only and only moving in the x direction. In case if you are wondering, we'll just be using multiplication and stuff like that. Sadly not. We're going to be using partial differentiation and a lot of really complicated math topics. So if you don't know trigonometry and calculus, you will not understand a lot of the things that I'm going to be dealing with, because we are going to be differentiating terms. We are going to be looking at sinusoids, sine functions. We're going to be looking at all of those really complicated math topics. But if you still don't know, I will break it down to a significant level that you will be able to understand it. But just a heads up. But if you know calculus and stuff, it's gonna help you out. So what does the Schrödinger equation actually do? Why is it so powerful? Why do we actually, even if you are little in science, you might be knowing this. Now, the best thing about this equation is that this equation can help us solve a lot of mysteries. So let me actually explain to you how this can work. So let's just say this is a box. I have this particle in the box. Now I threw this particle in the box, and when I'm saying particle, I mean electron or a quantum system. So let's just say this quantum system is an electron. Now this electron is free to move in its x-axis, and this box extends for infinity in all of the directions. Now, in case if you are wondering why infinity, quantum tunneling can take place, where if the particle can accumulate a specific amount of kinetic energy, it can not exactly break out of the box, but it can pretty much avoid of the walls of the box, even though it goes to the walls of the box and it can end up on the other side of the box. And that's why we pretty much just extend all of this to infinity. And we also say that so now we want to know where in the entire box can we find the particle, and that is where we can use the Schrödinger wave equation. Now the one of the most complicated forms of the Schrödinger wave equation looks something like this. Don't worry, we're not going to be solving this one, but something similar to this one. Now this is surely something really complicated. You won't have seen anything like this in your life, and this equation is actually, I wouldn't say unsolvable, it can be solved, but only for a few atoms. The reason is that this symbol that you could see over here, it's called the Hamiltonian operator. It is now this operator accounts for the energies of the particle. Now the problem with this operator is that more the electrons in the atom, the complicated this operator gets. Like even if you are trying to do it for a neon atom which has got an atomic number of 10, so we got 10 electrons, 10 protons, it gets very complicated. So if you actually try to do it for like some really complicated elements like uranium, technetium, you do it for like some really complicated elements which have huge atomic numbers like 40, 50, 60, the Hamiltonian operator will pretty much be like, it will take you, not even you, even a computer, hundreds of thousands of years to solve it, which as we know it is not possible. So that's why. So what the equation is doing is that it will calculate the probability of finding the particle in the box, and the symbol that we use for that is this symbol. It's called the Greek symbol psi, psi. It kind of looks like a pitchfork, but that's how it looks like. So let's actually dive into the derivation of the equation. Now, heads up, we're going to be using partial differentiation, and some of the things like the e's in the sum is not the e that we use in calculus. It is different. We are using this in physics terms, not like pure math. So it's just a heads up that I wanted to give you before I started up with the differentiation, because like some people will think that differentiation is incorrect. It is correct, yeah, if you would be really like, if you would have done only like calculus with math, yes, then you would think it is incorrect. Like I don't blame anyone, but just in case, just that one heads up, like because I looked up, like I checked it online, so if there was any issue with the derivations, it is correct, just that one heads up. So I'm just gonna get rid of everything so we can get a fresh page to start with. Okay. Alright, so what I wanna do is, the thing is, the psi value comes with, it's only made in a specific way. So the value of psi is equals to e to the power of I k x minus omega t. Then what we do is we will differentiate psi with the respect of x, so we get I k e I k x minus omega t. Then what we do is we will differentiate it again, so this is calculus, just in case if you don't know. Del square psi over del x square is equals to I k square psi, because e to the power of I k x minus omega t is equals to psi. So therefore we don't need to write it in that way, we just write it as psi. Next what we do is we know that the k is equals to p over h bar square, where p is momentum, h bar is the reduced Planck's constant, which we do it as h over 2 pi, and h is the original Planck's constant, which kind of relates to the energy of a photon, which is a particle of a light. That's a lot to grasp, you don't need to understand it. So what we can also say is del square psi over del x square is equals to p square over h bar square psi. And okay, no, I don't want to do that, sorry. And then what we can do is we can take the entire thing and put it in the side of the derivation. So h bar square del square psi over del x squared is equals to negative p squared psi. And then we can just use the thing of energy, which is potential energy plus kinetic energy. So we can just get it as E of psi is equals to p square psi over m plus u of psi. So therefore we just get it as h bar del square psi over del x square plus u psi is equals to e psi. This is the formula we're going to be getting the answer of in this video. The time independent Schrödinger equation. Looks complicated, is complicated, but don't worry, we will do it. So let's just get rid of all of them, so we can start fresh and get the differentiation done. Now I know some of you might not have understood what I did here, like how did I get the value, this long equation with just one value literally. That is the power of calculus. I can't say anything else. Okay, apparently I'll just have to erase this part. So I'm just gonna erase it real quick. Alrighty. Now let's actually go over the solutions of the equation. Let's actually calculate the wave function and the probability. And by the way, the probability is called the probability distribution. So negative h bar square over 2m del square psi over del x squared plus u psi equals e psi. Now the u psi we will take it as 0 because otherwise we will have an infinity to deal with, and I don't want that. So negative h bar squared over 2m del squared psi over del x cube. I'm sorry. Okay, I just made a little mistake over here. Get rid of the dels. I will need a d plus 0 is equals to e of psi. Next, what we will do is we will take all of the terms and put it in the respect of e. So we just get it as del squares. Oh my god, why am I writing it as del? It is a d square psi over dx squared is equals to negative k, okay, negative k square psi. Now we are going to be using a sine function, so using a sine function or a sinusoid, whatever you want to say, and then I can just put in that sine function. So what I can say is that psi is equals to the sine of negative kx, or psi can also be represented as the sine in a more elaborate form as the root of 2me over h bar x, not that x, that's a 3 x. And then what we can do is we can differentiate the sine function. Now the derivative of sine is equals to cosine, and the derivative of cosine is negative sine, and since we are differentiating sine twice, we get the answer as negative sine. Yeah, negative sine. So what we can do is we can say del square, oh my gosh, why am I doing it like again and again? D square psi over dx squared is equals to negative sine and kx minus omega t, and we can just do the same thing for this one. So we can get a negative sine, and we can get, and instead of using an x we can use a radian and call it pi. So the answer that we will get will be psi equals to the sine of root of 2me over h bar pi The boundary condition will just be that on the first boundary we have 0. Second boundary A, we will pretty much just we'll replace the H and we will add a M and the A over there. So we can add the differentiation of the second one in there. So we can just get it as something like this. Just a second. So we can just get it also like the d square psi over dx squared can also be written as h bar squared psi. Actually not psi. It should be pi squared over 2ma squared. So then we can normalize the entire thing and we can just get it as psi equals 2 upon a sine of pi x upon a. So then psi is not equal to the probability distribution. Psi square modulus is equal to the probability distribution. So currently if we plot psi, it will look like this. So then we pretty much square mod it, and this is at the lowest energy state, for just to say. Okay, that was incorrect. Alright, it will look like this. So we have the greatest chance of finding the particle over here and the least chance of finding it over here or here. So that's the entire Schrödinger equation. It was complicated, but we did it. And this is the entire kind of derivation thing, just showing you again. It is pretty complicated, but I hope you enjoyed it. This is a pretty different video, but I thought that if I'm gonna be coming up with quantum computing videos, which will take some time to come out since I am still learning it, so you should expect one, but like when I can't be sure. So I hope you enjoyed it, and I'll see you in another YouTube video.